Alright, time for another draftphysics.com video presentation. So we will pass on the counting the days to accept the paradox, okay, of pendulums and their interactions because, well, frankly, we need real evidence. And we don't have real evidence. We just have, fudgy, foggy, not very good, you know, illustrations. I've made so many arguments, and none of them have been dissected individually as I would prefer it be done. And it all starts somewhere, and they're all have different significance. So the idea, okay, so the new thing I will start. Let's see how many people will concede that gravity is a time-dependent force. That the whole way you defeat gravity is to not be exposed to it too long. So it's like the sun, okay, the same kind of force as sunlight. And it's really just matters, if you're tannable, how much sun you're exposed to. And so if you can move from one house to another house very quickly, you won't get hit by many photons. If you go very, very slowly, you get hit by a lot. So this goes to, physics has a work equation that basically says holding something against gravity isn't work because you're not moving it any, right? So they only count work as motion you can see. Now, you could even argue that they should be able to say, yes, this is work, because they should be able to know that it's not staying still. And I am actually doing real work in the fact that I have to push against gravity, and the falling part, I don't get it back. Okay, I'm not a spring. So when I push up, I have to do work. When it pushes back down, I don't get the work back. Okay, it doesn't reset my spring and give me power to push it back up again. Yeah. But anyway, they're not sophisticated enough for that argument that you can't actually keep something still in gravity, that you do actually jitter in gravity. That we are actually moving up and down in gravity. That's why your ass gets sore, is because it's going up and down. It's bouncing in the gravity. But anyway, so I've made lots of different arguments trying to illustrate that this is where the first mistake is made. I could argue, okay, so right back to Leibniz. And so we'll talk about Leibniz and his misunderstanding, okay, just a fact, and his misdefinition of a fact and a reality, and that wrong premise is everything. That's how all of this mold called physics grew, was out of one little misunderstanding. One little misunderstanding, and the monster of crap grows. It's the bad seed. The bad seed is planted, and the weed takes over the garden. Whatever you want as an analogy. Alright, so his axiom is, it takes the same power to raise 4 pounds 1 foot as it does to raise 1 pound 4 feet. That's his axiom. This is his writing, so I'm just saying this is right from the source. And this really is the entire substance of his argument, is in that statement. So I will illustrate that statement and point out how you can know it's not right. And I'll explain the continuing argument where he just makes a second mistake. Okay, and then it goes on from there. Mistakes lead to mistakes. All right, so 4 times. Okay, so we have 4 pounds. Okay, dropped 1 distance. Okay, is the same as 1 pound dropped 4 units of distance. Alright, that's his argument. Now you can know right on its face it's not right, because we know this is twice the velocity, so it's 1 times 2. Okay, and we know this is 1 unit of velocity, so that's 4 times 1. 1 times 4. And obviously those two answers aren't the same answer, so we're already in trouble. Now, if we put it on a lever, this is where it gets interesting, right? Levers are so interesting. Okay, so if we put the 4 pounds here, okay, and we're going to put the 4 units of distance away. The trick of the lever is, okay, is that, okay, so he's saying that, okay, I can put a 4-pound weight right here, all right, and what will happen, you know, in this case, the two will be equal. I can lift the 4 pounds, okay, from a deficit to the neutral position. But let's just say we're just using any force, and we're just going to lift the 4 pounds a specific amount. So we're going to lift it to this height. Well, we know this is 4 times the distance, so we're going to be lifting this one 4 times the height. All right, so he's basically saying the same force will do that. And that is absolutely correct. So I put the same force in here, and this will be lifted 1 unit of distance, and this will be lifted 4 units of distance. But the catch is, right, and I didn't even realize this myself, I should have made this argument in the past, the catch is this will be going 4 times faster. This is 4 times the velocity. You know, twice the distance would be twice the velocity. So the catch is you're not moving the object at the same speed. And what does that mean? Well, it means it's going through the gravity much faster. So it's getting here, okay, fighting less gravity. So that's the key to the whole thing. You know, it's 4 times the distance, but at 4 times the speed, it equals only 1 unit of gravity, essentially. So the fact is, the lever's trick is that it increases the velocity. That means the time it takes to get it lifted. So it's really lifting it at a speed, right? The 4x speed means that if I did launch it, it would go up and up and up and up 16 units of distance, right? Or 8. 8, right? 4 would be 8. Yeah, so it'd be 8 units of distance, right? Probably doing that wrong, but I have to, you know, you always have to think about what you're doing. It doesn't matter really. For the purpose of this part, the illustration is just to point out that clearly 4x the speed, all right, is not 2x the speed. It's not this falling speed, all right? You're defeating the gravity because you're in this short amount of distance, you go fast enough to only be in the gravity 1/4 of the amount of time, right? Per foot. You know, I mean, obviously it takes you exactly the same time. This is the same time as this, but obviously the increased distance, the 4 times the distance, mean you're going 4 times faster. So you're only in the gravity the same amount of time. So the huge advantage this thing has, this 1 pound out here has, is that it's only in the gravity the same amount of time. It's only fighting the same amount of gravity. Even though it's going more distance, it's only in the gravity for the same amount of time. And that's why the lever, that's the advantage of the lever, is it's completely, the advantage is all made out of the fact that if you move something faster, okay, you will defeat the gravity for the distance you traveled. Now the catch is that yes, this has, you have now put into this object more energy, and it certainly will show that by going much, much higher, much further into the gravity. You'll have this much higher velocity, and it'll go much further than just 4 times the distance. 4 times the velocity will get you 4 times the distance. So it's twice this 2x velocity, so it'll be 8. So that's the catch. That's the thing. That's what makes levers work, is they increase the velocity, not show you the distance. So even though it's not going the 8 units of distance, it's doing the 4 units in the speed of 8 units. It's increased the velocity, which decreases the amount of work you have to do on the object in the distance you're traveling. So in this distance that travels, you know, that the lever moves throughout that whole distance, its speed means it's fighting less gravity than it would if you moved it slower. If you moved it at the same speed that the 4 pounds is going up, then you could say, okay, they're equal. But it's not equal when you recognize that you're lifting this one much faster. Okay, even though the total time is the same, the velocity is different, and that means the amount of time per foot is way different. It's probably a better way to say that. I don't know if it's worth just redoing it different ways to see if you get the catch. But the simple argument is, well, I'll do the spaceship one. That's always the giveawayer. So we'll do that and see if that one impresses you. Yeah. Because I can probably get a physicist. We can probably, if somebody can push physicist Michael to actually answer the question, he'll make it clear that, yeah, the truth is, all right, that these two things don't have the same energy. It doesn't take the same power to lift the 4 pounds 1 foot as it does to lift the 1 pound 4 feet. This, okay, to be equal, you have to lift this one 8 feet. Alright, I'll be back. Alright, back. So, simple argument again, spaceship. And you're going to navigate it by throwing stuff, thrust, out of your spaceship. So you throw the 4 pounds, okay, going 1 velocity, and you throw the 1 pound going 2 velocity. That's 4 times the distance. It's only twice the velocity. The 1 pound going 2 velocity. And so I think physics Michael will agree, if I did do that, I haven't created an equality here. I have much more thrust. I have pushed this way. So I'm definitely going to move this way. I'm going to be compelled. All right, the spaceship will be compelled to move in the opposite direction. Because this is much weaker. This is half the momentum, okay? 1/2 the momentum that this is, and momentum does move spaceships. Okay, so kinetic energy doesn't mean anything. So even though the kinetic energies are equal, the momentums are not, and it is momentum that moves spaceships. So again, it's another pretty decisive argument that you have to sort of concede that your kinetic energy doesn't mean much if it can't move a spaceship. So, but it clearly it proves basically, if you concede this is the truth, then you sort of have to concede that Leibniz was wrong to say it takes the same power. It takes the same power to move this 4 times the velocity, not just twice the velocity. That's the same power. So if I throw the 1 pound out at 4 times the velocity, what the lever will produce, which is 4 times the velocity, then the spaceship stays going straight. So this is, again, all right, this misinterpretation of what gravity is. So just do it one more. Done it so many times. But, I mean, it's, you can understand it as just this simple. I mean, how many times do I have to say it over and over again, and you won't, nobody will make this brilliant counter argument how it's about these little units of distance, when you're going half the speed right here, that in the whole voyage you're only going to get twice the velocity. This is only going to take 2 units of time, and you will weigh twice as much. I mean, those are a lot of really important twos. All right, that you're just saying, I'm not going to, so what, 2, I don't, you don't like the number 2, and you're going to sit there and pretend it's about this 4 stuff. I mean, half the velocity is here. How can you basically say that this, all right, this did half the work, and then this does the other half of the work, when you can logically know this did the work here. This was work, okay. Gravity worked on the object, produced a velocity. This was no work at all, and that this really is your second unit of gravity. These are just 4.9s, in a practical sense, and you're going to end up with, because of the 9.8, you get your 9.8 here, and you get a 9.8 here. You get two 9.8s, it comes out to 19.6. That ends up being your velocity and your distance in this case. And that's what you get. And it's just clear, it's not linear. I mean, it's half the speed here. It can't be called linear, in the sense that you're not getting the same per unit. You're doing half the speed here. So obviously this was diluted. And what was it diluted by? What caused the dilution of these units of distance? The obvious answer is you ran faster. You ran through the gravity. The gravity had the same time here and the same time here. These two things take the same amount of time. This distance is the same amount of time as this distance, clearly indicating it's a time-dependent force. Clearly indicating that, as stated, you can think of it as raindrops, you can think of lots of things, and they're going very fast, speed of light. Think of a river going the speed of light made of, I don't know, little styrofoam balls. And you jump into the styrofoam ball river, and the little balls hit you. Each time they hit you, they give you motion. And eventually, you'll be going the speed of light, if they can hit you, with enough of them. But you're going to collect their energy as you go, and each time one of them hits you, it sticks to you. You've absorbed its velocity, you're sharing its velocity, and so you're gaining velocity with each time one of them hits you. You're absorbing the energy. The bowling ball, when it hits pins, the bowling ball gives away its momentum. It slows down, the bowling ball speeds up. Proportionally, all the momentum in the bowling ball eventually ends up in the pins. Alright, I'll do the one other argument. Well, you can just keep going with the argument. So I'll do the drive-by argument, and then I'll do the rolling argument and say, come on. Not one of you will concede. There's all kinds of evidence. It's a time-dependent force, not a distant-dependent force. None of you will concede. There's good reason to believe. All right, back again. All right, you have a gravitational body, and you're just going to mark a distance in space with little satellites, and you're going to travel that distance. Okay, you're going to go across that distance. And there is gravity, okay, moving you towards that body. And the simple truth is, what's going to happen? Well, if I go really slow, I crash into it. If I go a medium distance, then I'll get bent by it, but then I'll just keep shooting out. And if I go fast, then I get bent less and less and less. So the faster I go, the less the force bends me. So what's the key factor? Is it distance? No, not this distance anyway. Now this distance, okay, is the same as the gravitational distance. I mean, your motion is going to be acquired in this direction, okay, by the simple rules. Well, how long am I in that gravitational field? So the faster you fly by something with gravity, the less you get bent by it. I mean, it seems so obvious that it's just about how much opportunity this force has to hit you. The less opportunity you give the force, the less velocity you get in that direction. And the more opportunity to hit you you give the force, the more, decidedly more, you are bent. Kind of obvious. All right. So then the rolling thing. Now, I haven't seen this mentioned by Leibniz or de Charolais, frankly, but I don't have a perfect memory. But I'm sure someone in history has used this argument that I give the same mass, okay, I give this twice the velocity, and it will roll 4 plus the distance. Actually, no. it will roll at least 4 times the distance. And the simple argument is just the gravitational argument. What's causing the friction with the surface? Well, gravity is. The surface is touching based on gravity. Gravity's pushing it in. And so obviously when I'm going very fast here, my velocity is at its peak here and it'll decline as I go. And what's going to happen on that curve is that again, okay, that little half is going to pop up in this funny location. I'll be going half the speed here. Alright. That's how I'll lose my energy. So I'll lose half my energy here, and I'll lose my other half in this little bit. And again, it's the same time argument. This time will be the same as this time. You know, whatever, it doesn't matter what it is. It'll take the same amount of time to go from here to here as it took to go from here to here. So again, the argument is obviously it's being controlled by gravity. Gravity is a time-dependent force. All right, this is the same unit of time, so you're lost. Of course, the half is here because yes, you got half the pushing here and half the pushing here. You were pushed into the surface the same amount here as you were pushed into the surface here. So this whole path, you were pushed, you know, little bits, and here you were pushed a lot of bit per foot because you're on the foots longer. You're in a piece of distance a longer amount of time. You're on a piece of distance a shorter amount of time here. And so it clearly explains why there's this 4 times the distance is because it's the same rules as gravity. I'm cutting the friction way down here. I'm getting a nice free ride from the high velocity. And here I'm paying a high price. So you could understand that it's going 1 velocity here and it's going 1 velocity here. So you've 1 velocity here. So this experiment is exactly the same as this experiment. And this gigantic experiment is exactly the same as this one. So it's only 2 units of friction. It's all you really experienced. So, you know, but you got 4 units of distance because of the distribution of the force. So, yes, you were hit by twice as much gravity, but you were hit by it, okay, non-linearly, and so it's only 2 units of gravity defeating your twice the velocity. Yeah, so is there anything, I mean, like I said, this should be really, this should give you people some reason to say, yeah, I get it. It can't really be linear if I'm going half the speed here. This can't be the same as, you know, that in the sense that per foot it can't be the same. Half the speed here means that, yes, this was only half the friction, right? So you can understand that only half the friction happened here, and the other half of the friction happened here. And that's all there were with those 2 halves. Those 2 components. Alright. It's a little bit, yeah, well, I could have fixed that, but I didn't. A little bit of glare showed up. Anyway, yeah. See if I have anything to sum up. Alright, I think I'll reiterate the spaceship point, just because that's the one we have gotten physicist Michael to respond to. Really gotta fix that. Maybe if the light's on, it's probably still not good enough. That should be good enough. Alright, so spaceship again. Alright, so he has conceded the kinetic energy argument in some respects, in the sense that he's conceded that it doesn't move a spaceship. So in this example we gave of the 4 pounds, okay, going 1 velocity, alright, and we have a 1 pound, alright, going 4 velocity. Oops, 2. That's Leibniz's example. He'll concede that even though the kinetic energies here are the same, alright, because you're squaring the 1 and you're squaring the 2 here, blah blah blah. So the kinetic energy says it's the same. Now let's understand what the kinetic energy says. All right, let's get that part right. And the momentums are uneven. So, okay, over here you could say you have 200 momentum. All right, 200p, and only 100p is over here. And the kinetic energy says 100 and 100. Okay, so that's the difference in the philosophical or scientific definitions. And he's conceding basically that this number, this is the important one for thrust, is the momentum. All right, and so, but what does it mean when they say this kinetic energy, right? These aren't fake numbers, okay? This isn't made out of nothing, kinetic energy. They call it a joule, and understand that joules are converted into watts. And watts are real. I mean, you experience them in your real life all the time. I mean, joules are kind of, well, whatever a joule is, but a watt is real. A watt can convert it directly into heat. So that's the thermodynamic element. You can convert watts into heat units. And so he's basically conceding that they're saying there's the same heat going out both sides, but he knows there's not. He knows it's not real heat. He knows that this number, okay, where these two things say this is the same, 100 heats, okay, it's not the same heat. He knows it's not the same energy really in the universe. So that's where it gets all kind of broken, because yes, you can also do the same conversion. I mean, you can convert, these Newton things, okay, these foot-pounds numbers, the momentum numbers, you can also convert them into heat numbers. And that's the joke here. And these are the real heat numbers, and these are the kinetic energy ones are the fake ones, quite obviously. So when they say this has, like the bullet has 2,000 joules of energy, right, when it leaves the gun, and their gun only has 2 joules of energy. Well, when they say that crazy crap, this isn't real. It won't turn a spaceship. He's conceded the argument. It won't turn it. Okay, if I shoot the gun out one side and I shoot the bullet out the other side, the spaceship doesn't turn, because these 2 joules somehow mean something a lot. They mean a lot more than somehow these over here. So again, just change this to watts. 2,000 watts of heat go out this way. 2 watts go out this way. We know that if I actually did that, if I actually expelled heat, because heat will move a spaceship. So if I actually did expel 2,000 watts of heat this way and then only 2 watts that way, I'm radically going to turn. I mean, I'm going to turn the opposite way of that 2,000. So we know this is, come on, which one seems more broken? Reliable momentum, okay, dependable momentum, or this made up stuff that says there's 2,000 joules that don't turn a spaceship? I mean, if the energy, if the heat can't turn a spaceship, it can't move matter in space, where it's free to go anywhere, where there's nothing in the way, if it can't do that, why would you even think of it as energy? Because it can't do any work. The momentum can do work. The kinetic energy can't. You're not going to concede that's a problem for your argument? Anyway. Alright, so I'll call it a video. So anyway, so that's, eventually I want to, it really is a stage of arguments. I mean, it all starts with Leibniz looking at that 4 times the distance thing and thinking that's all there is. And then thinking that a lever, when it lifts something, that it isn't changing the velocity that you're lifting at, which is just the key point. It's not just lifting a distance. Yeah, it only lifts it, okay, 4 times the height. But it gave it the velocity to go 8 times the height. It lifted it at a much higher velocity. That's the fact. And so if you were to release those items and let them move, the 4 pounds will go 1 unit of distance. The 1 pound will go 8 units of distance. So you actually did a lot more work a lot more work than you saw in the initial movement of the lever. How far the lever actually moves isn't telling you how much energy it put into the object. in the sense that the lever's motion is again, you know, it's going 4 times the velocity, not twice the velocity. Dropping from 4 times the height is only twice the velocity. Lifting on a lever at 4 times the velocity is really 8 times the height. All right, so that's probably enough. So, so yes, you know, I mean, I've done the 13 videos. People won't pay attention, so I guess I have to like redo them in sequence or something. But they're all good arguments, and none of these arguments have been challenged with anything, any counter drawing of the reality. Nothing. 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 So we'll call this day 1 of gravity is a time-dependent force. Yeah. Demonstrate otherwise.